Okay, hi guys. So in this lecture, we'll be continuing on seeing some theory on the first equilibrium point and second equilibrium point. But before that, let's actually do some hands-on practice or some questions on the theory which we have discussed so far. So let's get started. So the question is 50 ml of a solution containing 1 gram each of NaOH. Then we have 1 gram of NaHCO3 and 1 gram of Na2CO3 was titrated with 1 NaHCl solution. Calculate the volume of HCl. We have to calculate the volume of HCl, which is needed only when phenolphthalein is used as an indicator. Okay, so in this case, if only HPH is used as an indicator, then obviously the conditions would be basic because this is an acidic indicator. Okay, so pH range would be from 9 to 10. So in that range, only the first equilibrium point will come. So as a result, what will happen is, in first equilibrium point, NaHCO3 won't react with HCl, only NaOH and Na2CO3 will actually react. So N factor, so what are the total milliequivalent of NaOH plus milliequivalents of Na2CO3, where N factor of Na2CO3 would be 1, as Na2CO3 in basic medium would be converting into NaHCO3, hence the N factor of both would be 1. So this would be equal to millimoles of NaOH plus millimoles of Na2CO3. So as we know that millimoles of NaOH would be nothing but given mass of NaOH divided by molar mass of NaOH, which is 1 by 40. Okay, so as it is used as millimoles, we have to multiply it with 1000 plus millimoles of Na2CO3 would be given weight of Na2CO3 as it is 1, and the molar mass of Na2CO3 would be 106. So how did we get there? 23 into 2, which is 46, plus carbons 12 plus O3 is 48. So 60 plus this is 12 plus 48 is 60, and 46 plus 60 would be 106, would be equal to normality of HCl into molarity of into volume of HCl in milliliter. This is the millimoles. This is multiplied with 1000 here because this is the equivalents, and multiplied with 1000 gives milliequivalents of Na2CO3. So from here, volume of HCl that is required can be calculated. So second case is when only let's say only methyl orange. First HPH is used as an indicator, and then methyl orange is added after first equilibrium point with HPH. So what will happen in that case is, first Na2CO3 would be getting converted into NaHCO3, and NaOH would also be reacting. So these two at first equilibrium point would be there, and at second equilibrium point what will happen is, the NaHCO3 which was formed in the first equilibrium point would be getting converted into H2CO3, and NaOH won't be there as it was already been converted into or rather was already fully utilized at the first equilibrium point. So this was the NaHCO3 from the first equilibrium point, and we also have a NaHCO3 already present in the mixture. It is the original NaHCO3, the 1 gram which is present originally here. Okay, so at second equilibrium point what will happen is, so this won't be there, only this one and this one would be there. So we have to add the milli equivalents of NaHCO3 from first step plus milli equivalents of NaHCO3 which is originally present. That should be equal to the milli equivalents of milli equivalents of HCl which is needed in extra quantity. Okay, so total that would be required would be so that in that case it would be nothing but milli equivalents of NaHCO3 in the first step would be equal to milli equivalents of Na2CO3 that reacted to form NaHCO3, so that would be equal to milli equivalents of Na2CO3 consumed in the first step plus milli equivalents of NaHCO3 that was originally there. Okay, so milli as n factor of Na2CO3 in the first step would be 1, and in the second step NaCO3 the n factor is already 1, so this would be 1 upon, so this is just equal to millimoles. So millimoles of Na2CO3 would be 1 upon 106 into 1000 plus 1000 into what would be the equivalence of NaHCO3? It would be 1 upon 84, which is nothing but 1 upon molar mass of NaHCO3. Okay, so this is the case when methyl orange is used after the first step. Okay, so this is the extra amount of HCl which is needed, but the second question says that how much HCl solution is used after the first reaction, after the first equilibrium point. So we don't need to add the HCl which is needed in the first step and plus the HCl which is needed in the second step, as the question itself says that methyl orange is used after the first equilibrium point. So after the first equilibrium point, what is the volume of HCl needed? So volume of HCl needed would be simply this would be 1 into V. You can just calculate it. Okay, so next is only methyl orange is used from the beginning. So from the beginning, how much volume of HCl is needed? Only methyl orange is used from the beginning. So from the beginning, if only methyl orange is used, then that's a different story here. So what will happen is the NaHCO3 which was originally present in the mixture would react with methyl orange and Na2CO3. The n factor of NaCO3 here would be 2, because at first equilibrium point won't be there, so NaHCO3 won't be formed here directly. Formation of H2CO3 or carbonic acid would be there, so directly it forms H2CO3. So n factor here would be 2, and NaOH or other NaOH which would also be reacting with methyl orange in acidic conditions, which is below 5. Okay, so in this case only methyl orange is used, hence we can write that milli equivalents of NaHCO3 that would be used would be n factor into millimoles. N factor is 1, millimoles would be 1000 multiplied by 1 upon 84. Okay, and milli equivalents of NaH2CO3 Na2CO3 rather would be 1000 into millimoles. Millimoles would be 1 upon 106 into n factor would be 2, and milli equivalent of NaOH would be 1000 into number of equivalents of NaOH, which would be nothing but number of moles into n factor, which would be 1, so that would be 1 upon 40. So volume, so we just add all the milli equivalents required, so it would be 1 upon 84 plus 2 upon 106 plus 1 upon 40 multiplied by 1000 would be equal to 1 times V. So this is the volume of HCl which is needed in this case. Okay, so you can calculate all the volume required in the first, second and third step easily. Next, let's discuss another important topic which is called hardness of water. Okay, so hardness of water, first let us define what is called a soft water. So soft water is nothing but when soap or detergent is mixed with water, foam formation takes place. Okay, so if that is the case, then that water is called soft water. When soap or detergent is mixed and water turns foamy, then that water is called soft water. And hard water is just the opposite of that. When soap and detergent are mixed in the water, water does not turn foam, or foam formation does not take place. No foam formation takes place on adding detergent or soap. Hence that type of water is called hard water. Okay, and so let's actually discuss some important compound here based on the topic of hardness of water, which is nothing but sodium stearate, which is C17H35 C double bond O and A. Okay, and which actually dilutes or dissociates as 2 moles of, on adding calcium, it undergoes this reaction, not dissociates, it undergoes some reaction on adding calcium, that it undergoes C17H35 C double bond O whole twice Ca plus 2 moles of Na plus into 2 is attached with calcium here, plus 2 moles of Na plus is formed. So we'll be continuing on seeing more on the hardness of water in the next lecture. Till then, good luck and goodbye.